there are some errors that we did in the last derivation. I will come to those errors very soon. But I realized that I need to give you a bit of a background about Dirac delta function and autocorrelation. Okay? You remember those? Because I received a lot of questions after the course, so I think it's going to be useful for you. So this is a page that is between, like, we will come back to where we were. So we go back, okay? So Dirac delta function. And this is not super rigorous. Dirac delta function is a weird function, so don't expect me to be super rigorous here. But one way of thinking about Dirac delta function is to remember normal distribution. Okay, let me write it down for you. So fx is, let me just switch to blue. Fx is 1 over sigma square root 2 pi. This is just a Gaussian distribution with 0 mean. What I've written is this. Do you have any question at this point? No. So now, if you take, so just quotation, okay? If you take limit of sigma to 0 of fx, so you are basically squeezing the Gaussian function, okay? Narrower and narrower. What happens? It becomes higher and higher at 0, right? But the integral remains 1. So this is Dirac delta function. So basically this looks, the normal distribution looks like this, where this one is sigma, right? Not that one, rather, oops. No. Okay. So approximately this one is sigma, right? So we are taking it smaller and smaller until it becomes something like this. And this part goes actually to infinity. Okay, but I'm not showing it. Usually Dirac delta is shown by such an arrow. Yes?
Can we consider the half maximum?
Yes, half width at full width at half width at half maximum. Yes. Not exactly half maximum though. I forgot the properties of Gaussian. Can someone remind me? So what Yusuf is saying is that if you take this height right in the middle and measure this, is it going to be sigma? Alper?
No, it will be e to the minus 1/2.
Oh yeah, right? E to the minus 1/2 divided by square root 2 pi, and it's not necessarily sigma. Let me think about it. No. Whatever, okay? No. This is very important. Okay, let's find it. So we want to know what will happen when 1 over sigma square root 2 pi e to the minus x squared or 2 delta squared is equal to 1 over 2, right? So what is that x? That is this x. So it's definitely not sigma, but it's like some number times sigma, probably. But there is also this definition of full width at half maximum. That's another way of looking at the Gaussian. Okay. But we do know that the standard deviation of the Gaussian will be sigma. If you do the standard deviation, it will be sigma. So we are squeezing standard deviation to 0, right? That's why our maximum point goes to infinity. Any questions? No. Now, the property of this Dirac delta is, one of the properties is that if you integrate it, you are going to get 1. So I want to talk about units here.
1 over x.
Exactly. So if this is meters, then this is 1 over meters. Because 1 is 1, it's a number. Okay? So if you have something like Dirac delta related to position, then this function has a unit of 1 over meter. If you have something like Dirac delta with respect to time, it has a unit of 1 over second. This is going to be very useful for us. Are you with me? Yes? Good. A more simplistic view of Dirac delta could be this. I think you can get away with it if you think of Dirac delta like more simplistically, like this. This is a over 2 minus a over 2. This height is 1 over a. So what is the area of this rectangle? 1, right? Everyone agrees with that. And as you take a to 0, you approach Dirac delta x. Okay? That's another way of looking at it.
Also, if we take any absolute integrable function with integral 1 and squeeze it, it becomes Dirac delta.
Okay.
There's nothing special about that rectangle
or Gaussian. Okay. So I didn't do any mathematical sin by doing this, right? It's just one of the possibilities. Another property of Dirac delta is this. Another property. So let's say you have a function. Okay, you multiply this function with Dirac delta. So this is Dirac delta. So this is Dirac delta of x minus a. So it becomes infinite at a. So this is the point. Oops, what happened? This is the point. Okay. I think I figured what was the reason. I think this should be this. Yeah, okay. This is the point where x is equal to a. Now, this is a function. The top one is a function. So if you integrate fx with multiplied with Dirac delta x minus a dx, some of you do know that it's going to give you fa. But let me explain why. Because everywhere else it's 0, right? So you are not going to get anything from there, except for the point where x is equal to a, where f is fa. Does it make sense? So it's basically, otherwise it's 0, so it's basically an integral around x equals to a, and at that point you can just take it out. I hope this is not a mathematical sin.
In order for this to be valid, f needs to be continuous.
Okay. Okay? F needs to be continuous. Very good. So you get the point that it's fa. Again, this function might have some units, and you can see that you get the same units at the end. So the units of delta must be inverse of the units of x. Okay? Any questions here? Let me give you a physical example, which is quite relevant to our model. Let's say you have a ball, and the ball has a mass m, and there's another ball here. This also has a mass m, and it comes with a velocity v. Okay? So what will happen when they collide? It's a head-on collision. Do you know by intuition what's going to happen, or from playing billiards? Nobody plays billiards anymore, right?
Velocities will change sign. Velocities will just change sign.
So
Depends on the angle.
no, head-on collision.
The momentum will transfer completely.
The momentum will transfer completely. So the left one will completely stop, right? The right one will have all the momentum, right? But what happens in between? We always take it as an instant. Let's say it happens in a time delta t. So while in that time delta t, the momentum is negatively transferred here. So there is a force here in this direction, and there is a force here in that direction. Action equals reaction, right? So we know that F times delta t is mv, right? So what is F then? If you take delta t to 0, as delta t approaches 0, F approaches Dirac delta t. Does it make sense? Of course, this time you are going to say, okay.
T times delta.
Exactly. F is approaching m times v times delta t. Now it's better. Sorry. So if you integrate over the time, because if you integrate, you are supposed to get m times v, right? And this is what's happening. But otherwise, let's write it again. Let's write it again. What is F? F is mv over delta t, right? And as you take delta t to 0, F approaches m times v times.
Instead, could we write that we can take the px moment delta t minus px moment 0 equals integral of f from 0 to delta t, and as t goes to 0, that would have been healthy writing.
Okay, let's do that. Can you assume that I did that? Yes? Good. Very good. So what we are doing is this. So at time t equals to 0, F started being mv over delta t, and this is delta t. And we are taking, so this is a function, this is F versus t, okay? This is times 0, this is delta t. Are you happy? So the area is always going to be mv, all right? But the shorter you take delta t, the higher the force becomes, okay? Very good. How about in our program? If you remember, we started thinking, so let's talk about impulse. So this thing is called impulse, right? Impulse is the change in the momentum. So let's remember what was happening in our code. In our code, there were these random kicks that were happening at a certain times. And we decided that we could model them as r of t. Okay? We did this. Now, let me simplify this a little bit. Let me simplify it. First of all, let's think about it as one dimensions. Just one dimensions. There is only one dimension, and there are kicks. The kicks are happening at particular times. So we are going to eventually get, so this is time. Let's say we discretize time like this. And the kicks are happening inside these times. Does it make sense? So if what we are modeling is actually the effect of all the kicks. The effect of all the kicks. Okay. Am I telling you this a bit in a bumpy way? Like, I think right now the knowledge comes to you as impulses, and hopefully at home you will integrate it into a Gaussian. But I want to the whole thing that we are doing today is to show you, for example, what we learned here. We learned that if I take delta t to 2 delta t, right, then the force in our model goes to F over 2. Do you see? Weird, right? In here, it's going to, in here, it's a different story. It's Gaussian. There are a bunch of impulses coming from all over the place. And if I, for example, the impulses will create a Gaussian, right? The impulses will create a Gaussian. So there is an impulse Gaussian here. But what if I start summing up? What if I take delta t to 2 delta t? What happens to this impulse Gaussian?
Standard deviation will double.
Okay, I'm really happy that you are wrong. I'm not happy at all. I'm just joking. So what is the distribution when you sum 2 Gaussian distributions? Because that's what another Gaussian. But what happens to its standard deviation? It does change. So do you understand the question, first of all? I have a Gaussian. This is my Gaussian. This is another Gaussian. What if I sum every number here and every number here? Okay, so I get n numbers here, n numbers here. I sum them up, I still have n numbers. That forms another Gaussian. So this has sigma, this has sigma. What is the sigma of the sum? Lower than sigma. Okay, let me. You are doing convolution, yes. And what is the result of that convolution? Good, so we are learning, right? Let me, how do I add page? No. Okay. So it turns out that if you have a variable x which has sigma x, if you have a variable y which has sigma y, then z, which is x plus y, have a sigma z, and sigma z squared is equal to sigma x squared plus sigma y squared. Interesting, right? I will not derive this, but you can easily show this. Not easily, I mean, you can show this. Okay. Do you buy it? It makes sense, right? There must be some quirk there. Good. So how does it translate to our case? The page is in the wrong place, so let me just reorder, and you think your answer. Yeah. How does it apply? So it turns out that if this has a Gaussian sigma, then this one has a Gaussian of sigma square root 2. Are you happy? Yes? Now, what was force? Force was so the sigma of the force was the sigma of the impulse divided by delta t, right? Now the sigma of the force, when it's doubled, so let me write it as R1, I1, R2 will be sigma of I2 over 2 delta t. What does it mean? It's going to be sigma of I1, sigma of I1 times square root 2 divided by delta t times 2. Do you see what happened? What happened is the following. Force, the sigma of this random force is proportional to 1 over square root t, square root delta t. That's what I'm trying to show you. Remember, at the end of the lecture, I told you like it's 2 k gamma kbt, but we also have to put delta t at the bottom of the square root. That's what I'm trying to explain you. Okay, let me show you a code. So this is an impulse code. So we have some mass, some gamma, some kbt, some delta t, and some number of points. Let's say we have p0, and these are, so impulse is change in momentum, that's why I'm going to talk about delta p, okay? So I write delta p as p0 times some random Gaussian, right? So the standard deviation of this function is p0, this delta p. Then what I do, I write r as r over dp over dt. So it will have some standard deviation, right? And I'm going to calculate it. Then I do the following. Then I introduce dp2, which is this thing. So I need to explain you what's going on here. Or if you understand, you can tell me. You understand. You don't understand. Let me show you my code. So let's say I have an array A equals to exactly, yes, that's what I want. It's reading my mind now. And I know I also want this. Yes, very good. What do I want? Yes, I do want this. Yes, very good. So I have 1, 2, 3, 4, or yes, 1, 2, 3, 4, 5 up to 10. Then when I do this reshaping, it tells me that I don't have NP. Yeah. Yeah. Do you see what it is doing? Basically, so if I reshape it like this, 5 to 2, it's going to give me the same thing. If I could do it 2 to 5, it's going to reshape this like that. Okay? The point is that when I write 5 here and minus 1 here, it will understand how much it would take at that column. So it will do it accordingly. So if I write 2 here, it will automatically replace the whole thing. So
if you write 3, will it give an error?
Yes, let's see. Yes. Okay. Are we happy? Yeah. So what? So I'm doing I'm doing this so that you remember all these forces that were happening at delta t times. Now I'm taking the first one, second one, third one, fourth one, and I'm going to sum them up. So I'm going to sum over every 2 delta t. Okay? That is going to be, so look, I'm summing them up over this axis 1 so that I take one string, I put 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, and sum them up so that it's 2 delta t now. That's how I get the impulses. My dt2 is 2 times dt, and my r2 is dp2 over dt2. So if I run this code, you will see that the standard deviation for the first one is around 2, while the standard deviation for the second one is around square root 2. Which means that as I increase it by twice, I get a reduction by square root 2. Are you happy? Okay, good. Any questions, comments? How can I show this hidden cell? Yeah. So now let me talk about autocorrelation, because that was another question that I was asked. So in what context did we see autocorrelation? We saw that RT plus delta t that's where we made a mistake, by the way. I think at some point, let me find that point towards the end, at some point I wrote that this is that, right? So that's a bit wrong. Or for example, so I will fix it. I'm actually going to use a letter for it. I'm going to use Q times delta t, Dirac delta t. So this is in Newton, this is in Newton, this is 1 over second, then this one is Newton squared times second. Okay? But let's try to understand what is autocorrelation at all. Okay, what do we mean by this Dirac delta? So what I will do is this. I will start, let me show it in the code. So I have here the same kind of a code. Now, let me just erase this part. So this one is uncorrelated. I just take the impulses divided by delta t and do nothing. So what is it? It's a random, as random as it gets from Python's libraries, right? Then how do I find autocorrelation? I basically do the following. I have a function that has a length of q, okay? Let me show it in here. So I have a bunch of r's. They are. I have to write it as dots because the moment I write it as a function like this, there is a correlation, because this point is next to that point. That's the point of no autocorrelation. Okay, no autocorrelation means that this moment and the moment right next to it has nothing in common. That's what this Dirac delta is telling us. Okay, so what I'm doing instead, so let me not plot it at all. Let me just take this as there is R0, R1, R2, blah, 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 goes to many, many numbers, up to RT. Then what I do, I land on one of them, and I basically take, let's say this is RT. I basically take from RT minus Q over 2 up to RT plus Q over 2. So I take Q points and multiply each point with that point. Multiply and write it down. So RT minus Q over 2 times RT. And I do the same thing for each one of these points over here. Does it make sense?
Yeah.
Then I shift this window as much as I can inside this force. And I sum whatever I get here. So what does it tell us? On the average, then I average it out. On the average, what is the multiplication of force at this time with some time before or some time later? Yes? What do we expect to get?
Here, 0.
Hmm?
In our case. In this case, 0.
0 where? Here 0, here 0, here 0, everywhere 0, except for here when it's RT squared. Does it make sense? So right at the point where we are, it's always going to bring positive values. But others are uncorrelated. So sometimes 1 will be multiplied with minus 0.1. Sometimes 0.7 will be multiplied by plus 0.3, etc. It's just two Gaussian values multiplied by each other, and then you take the average. The average is 0. So let me run this code. Do you want to see the code? Do you see? Does it make the explanation? Does it make sense now? So I start from Q over 2 all the way to T minus Q over 2, and each time I have this window of Q. Not my best day of teaching, but do you see this Dirac delta? Only at 0 you have a peak, but otherwise it's 0. Okay? Now let me introduce some correlation. This was uncorrelated force, and that's what we are working with. And you can see the uncorrelated force looks like this, not a smooth function at all. Okay? But now let me comment it out, and I start with all zeros in R, but this time, instead of just saying that RT is directly equal to dP over dt, I add the previous force, a bit of a previous force to this force. So it's a random number plus whatever I had here divided by 1 over 2. Random number plus whatever I had before divided by 1. Does it make sense? 1 over 2. Well, 1.2. I mean, depending on how small you take this number or how large, you can switch the correlation. So if I take 1.2, let's see the graph. Do you see the correlation? Is like that. So if I divide it by 2, the correlation is much narrower. You see? I decrease the correlation. If I divide it by 1, it's heavily correlated. Do you see the function becomes
It's almost like a normal function.
which one? This one. It's an accident. It's an accident. I can do it again, and it's like this. Okay? Are you still with me?
Yes.
It's sort of like a random walk. What we have here is sort of like a random walk. And it's correlated. Random walk is correlated with itself. Because you are somewhere and There's a randomness plus to where you are. But just random is uncorrelated. You see? Yes, very good. Okay. I think we are ready to fix our errors now. So, I think this is a bit dangerous, but it's okay. Writing it like that is a bit dangerous, but it's okay. I will tell you what is absolutely wrong. I hope I will find it. By the way, this is, as Alper told us, this is the homogeneous part. That's why it's there. Do you remember I was going to explain it to you? So you have a homogeneous and particular solution. At the end, you have to sum the homogeneous and particular position. Yeah. Okay. This one is wrong, probably. Let me see. Do you see what I have here? This should be Q times delta, and we will find Q soon. So this is wrong. This is wrong. This is Q. Okay? Because what I did there is I just said that this is R squared times delta. Do you see what I did there? And this is wrong. Why this is wrong? Because Newton, I write Newton times Newton equals Newton squared times 1 over second. Do you see? So this is Q, and this is Q. This is Q. Very sorry about it. This is Q. And finally, this is Q. Now, this is supposed to be, the 2 gamma kBt is supposed to be Newton squared times second. Do you agree? Let's see if the units hold or not. So what is gamma V? It's Newton, right? Do you remember gamma V was friction force? I have completely lost you.
We can see it from here. We can see it from the...
Yeah. So then gamma is Newton divided by meter times second, right? So what is kBt? kBt is joules, right? Which is Newton times meter. So if you multiply them, Newton over meter times second times Newton times meter is Newton squared second, which we wanted to have. Are we happy? Good. Then do we need a delta t over here? I think we need a delta t over here. So coming to here, it's this thing is q times delta t, and q is equal to that. Okay, so, and this is correct. This is correct. Okay, so everything else is fixed. Okay, something is running. What is running? Let's see what else do we have here. Okay. Did we talk about this code? Langevin dynamics. All the codes look similar, so you might be confused. But let me tell you what's going on here. We have some mass, we have gamma, kBt, delta t, t, number of time steps, etc. So we start with positions and velocities, and then I want to point out this part. So there will be kicks on the particle, but they will come from random angle that goes between 0 and 2 pi. and their magnitude will be this thing, like 2 gamma kbt over delta t square root times the Gaussian function. Okay? And then we just stack the magnitude times cosine theta is x component, magnitude times sine theta is y component. And the rest is just acceleration is gamma v plus force over mass. And this is x equals to x plus vt plus 1/2 at squared, and v is updated like that. And if you run this, you will get a very long run of diffusion process, right? Okay, there's one more thing that I want to tell you about diffusion. Do you want to have a break before hearing that?
We still have 9 more minutes.
Okay. Let me continue. But they are really tired. So let's have a break.